We will be doing this question number 32 in question number 44 in chapter 32 in Verma's book. We are given a cube A, B, C, D, E, F, G, H, and assume that there is a resistance R on each of its side, and then we need to find out the resistance between the diagonally opposite corners A and F. So before we do this problem, I wanted to show you a quick trick to draw the cube something like this. So basically what you do is you draw two kind of a like this, a slanted square, and then just join these points. You draw it real quick. This is the trick you need to do because you need to reproduce this when you are answering this question in an exam paper. So coming back to the problem, what is the resistance between this point and this point? If you observe closely, there is no simple and straightforward serial or parallel combination, because if let's say consider these two resistors trying to find out any parallel way or series way, we have a resistance cutting these two things, so we can't just really add them. There is no direct parallel. For example, this is not in parallel with this because they are in between resistors and things like that. So if this is a little bit of complicated problem, we could possibly solve it by setting up a voltage here like that I have done this, and then there will be a whole lot of number of loops. We will keep applying Kirchhoff's current law at all these junctions and Kirchhoff voltage law in that loop. And there are so many loops, the number of unknowns will be so many in the equation that it's going to be hard to solve it. It's best left for the computer and software to solve this kind of problem with large number of variables. But there's one trick in this problem, and that trick is applicable because they are given that all these resistors are equal. What it means is that this circuit is a symmetric circuit, and we are going to exploit that symmetry to find a simpler solution. So if you add a voltage meter here, we are trying to find out how much is the current flowing through this and passing through this, and if we can express this current in terms of only one variable, then we can apply the Kirchhoff voltage law in this loop and find the relationship between that current and the voltage, and then we can find the equivalent resistance. So let's focus on this particular node, the current entering on this node A and then going into three different parts and coming to the diagonally opposite thing. You can see that these three, as it enters from here and as that it comes out from here, these three currents are going to be exactly same. And the reason for this is that if you traverse this path like this here, and maybe this here, they are exactly same. But if you also look, this path, there's a path all from here, that also is pretty much same as this path, and you will have to traverse maybe this and this path to make it equal, or could be, for example, if you are comparing, depending upon which you are comparing this with this and this path. So basically, no matter how you look at this, if you're looking from A and going into these three branches, they are equal paths. That is one thing, and because of this, if there is current I flowing in this, then there is a current I flowing here and the current I flowing here. And there is another symmetry. Looking at the whole thing from this angle, now we are going to look the whole thing from this angle. So let's say if we reverse the battery polarity and put positive here, negative here, then there is a current going to flow from here, and that current will also be I and coming back to here. So by way of symmetry, we see that this I current entering into here should also be the I and I currents coming out of here because of this symmetry. There is one thing though you need to keep in mind. Instead of this F, if we have to find out, for example, the equivalent resistance between A and let's say C, then the current flowing out of this may not be equal, because while the currents here and here will be same, it will not be same current flowing out here because it will traverse a different path compared to these two. So those things you need to keep in mind. Now coming back to the problem, we have I current flowing here, and at this point, and there is a current I flowing here. Let's focus on this particular terminal, current I flowing here, and we know that the current that is coming out from here and out from here, they are symmetrical. They are coming from two symmetrical paths, like this, and this. Therefore, this current must have been divided by half in these two terminals. So you'll have a current half I by 2 here and I by 2 here. You could also do the same thing from coming from here, going into two different branches, and these two different branches are traversing equal and symmetrical paths. So the current will be equal in these two, and therefore half of this, or I by 2 and I by 2. So we have I here, I by 2 here, I here. We can in the same way find the current in all other branches, but we don't need to, because this one branch, this current in this whole section is good enough for us, because we can apply a Kirchhoff voltage law in this whole loop, and that Kirchhoff voltage law will be this voltage V is equal to the current drop here, which is I into R, plus current drop here, which is I by 2 into R, plus I into R. That becomes IR plus I by 2R plus IR, which is 2IR plus IR by 2, 2 into 2, 4, 4 plus 1, 5 IR by 2. 5 IR by 2 is equal to V. This is the relationship between the voltage and the current related to the resistor R. Now, how do we find the equivalent resistance between this point and this point? Mentally replace this whole thing, this mesh or a mess, with this one simple resistor R. If there is I current flowing, then the equivalent resistance R is given by the relationship V is equal to IR, or R is equal to capital I by V. And this capital I is nothing but I plus I plus I, or 3I. So the resistance R is given by capital V divided by I, and I is 3I. Now we know that we have already expressed this V in terms of Ri. We can write 5 by 2 Ri divided by 3 Ri. I cancels, so we have 5 by 6I. That's the whole solution of this problem. Any problem like this, you need to exploit the symmetry and distribute the currents and find the net current flowing through this, and express the resistance as the ratio of the voltage divided by the total current flowing on it, and then use those symmetries to solve the problem.